Hey guys, thanks for tuning in. I want to lay the groundwork for the in-class exercises we're going to be working on tomorrow on radioactivity and nuclear reactions. So this will help us hit the ground running tomorrow. All right, first we got to go over some of the so-called symbology of nuclear reactions. The subatomic particles are represented in this, nuclear format, and so we got to know what the numbers mean and how to represent each of the subatomic particles. So, first up is the proton. The proton is represented by the lowercase p, and kind of like when we did the nuclear symbols for the different isotopes, you've got a superscript and a subscript. The top number is the mass number. A single proton is considered to have a mass number of 1. And, that should seem pretty understandable given our discussion of isotopes. Unlike the nuclear symbols we used for isotopes, however, the subscript, when you apply it to subatomic particles, the subscript refers to the electrical charge on that particle. And so we know that protons have a positive charge of 1, and so the subscript is 1 for positive charge. So the neutron, you might guess, has a 0 here for the charge, because of course they're neutral, but they still have a mass number of 1, and we use the lowercase n for the neutron. You can probably guess what the symbol we're going to use for the electron is. That's right, E, lowercase e. It's got a -1 charge, and relative to, the electron, it does have a finite mass, but relative to the mass of the neutron and the mass of the proton, the electron, it has kind of a negligible mass, and so traditionally it's just symbolized with 0. Okay, so know these 3 symbols. We're going to have to use them quite a bit. Okay, now quickly I'm going to go down the list of characteristics for the 3 most common forms of radiation, alpha, beta, and gamma, in terms of these characteristics. Okay, first, alpha. Alpha radiation is a particle. It's in the form of a particle, and specifically it's basically a helium nucleus. It's represented by the lowercase Greek letter alpha, and it's symbolized using this nuclear notation. There are 2 neutrons and 2 protons in an alpha particle. So basically, if you take 1 atom of helium-4 and you strip off the 2 electrons, you're left with the helium nucleus, which is an alpha particle. So the charge is 2+, the mass is 4. Common source, radium-226. The penetrating power of most alpha radiation is pretty low. It's not a real dangerous form of radiation, and the shielding that's required is simply like a piece of paper or clothing. Beta radiation is also mediated by a particle, which in this case is the electron. It's symbolized by the lowercase Greek letter beta, and we saw this on the last slide. It can be symbolized using this notation. The charge is -1-. Even though we said it has negligible mass compared to the proton, the ratio of the masses of an electron to a proton is known fairly well, and it's basically 1 to 1837. Okay. A common source of beta radiation is carbon-14. So when you hear about carbon-14 dating of fossils, what they're detecting from the artifact is beta radiation. The penetrating power of beta radiation is moderate. It can actually penetrate, up to like half a centimeter, and so it is a some of it is a dangerous form. Some beta emitters are dangerous, and you have to be careful around them. Metal foil is usually sufficient to block beta particles. Now, gamma rays are much, much more powerful than either alpha or beta. And unlike alpha and beta radiation, gamma radiation is not a particle. gamma radiation is electromagnetic radiation. Okay, so it's very, very high frequency electromagnetic radiation, even higher frequency than X-rays. This is the lowercase Greek symbol gamma. There's no charge, no electrical charge at all, no mass. Cobalt-14 is a common source. It's one of the several sources of gamma radiation. The penetrating power is very high. It goes through the human body like a hot knife through butter. So gamma sources are very dangerous. You have to take a lot of precautions. It takes things like lots of, a thick layer of lead or concrete to block gamma radiation. Okay, now let's look in a little more detail about each of these types. So alpha radiation, in a picture form, if you have a heavy nucleus, like as we'll see uranium-238, when it decays radioactively, it will emit an alpha particle. Okay, here's an example. Oh shoot, I'm forgetting off the top of my head what Pu stands for. I don't know if you have a periodic table. Plutonium. Plutonium-240 will decay radioactively via alpha decay to uranium-236. And what I want you to notice here is, this is what we're going to have to pay attention to tomorrow, is sort of the bookkeeping of nuclear reactions. So if you start with plutonium-240 and you radioactively decay to uranium-236, then you can see that we've lost 4 mass units, right? We've gone from 240 to 236, and the atomic number has decreased from 94 to 92, and that perfectly corresponds to an alpha particle. Okay, so you can see that 240 minus 4 equals 236, and 94 minus 2 is 92. All right, so here's another example from scratch. All right, let's say I mentioned uranium-238. If we have an atom of uranium-238 that radioactively decays via alpha emission, then you're going to have, you definitely know you're going to have an alpha particle, right? Otherwise it wouldn't be alpha emission. So now, maybe pause the video, and I want you to see if you can figure out first, what would the element be? What element does uranium-238 decay into when it gives off an alpha particle? Okay, so I think in order to identify the element, you know that you're going to have to subtract 2 from the atomic number. So it's going to go to an atomic number of 90. And all you have to do is look on your periodic table and locate the element with atomic number 90, which is thorium, right? So there we go. And then you take 4, subtract that from 238, and you've got 234. So when uranium undergoes radioactive decay via alpha emission, then it converts from uranium into thorium. Okay, next let's see an example of beta radiation. So in beta decay, a heavy nucleus will emit a beta particle, which is an electron, as we saw. And this is a slightly bizarre, the mechanism for beta emission is kind of bizarre. It entails a neutron converting to a proton plus an electron. Okay, so whenever a nucleus undergoes beta radiation, the thing that's important to know is that you're going to lose a neutron and it's going to convert to a proton, and then it's going to eject an electron with a lot of velocity. So here, in using our nuclear reaction symbol, this is how we represent that beta radiation. So here's a neutron, and when it undergoes beta decay, it converts into a proton plus an electron. And you can see it makes sense, right? The mass, that we have conservation of mass, right? We had 1 mass unit to start, and after the transformation we still had a total of 1 mass unit. The net charge at the beginning was 0, and the net charge after the transformation is also 0. Okay. Here's an example of beta emission to give you some practice. All right, so let's say we have the iodine 131 isotope. This is an isotope that decays via beta emission. We know it's going to eject an electron, and so what is the new element and what is the isotope of that new element that results? So take a second and see if you can figure this out. Push pause. Okay, hopefully, first, don't forget, you have to remind yourself that this is what's going to happen inside the iodine nucleus. A neutron is going to convert into a proton. So is the mass number going to change? And the answer is no. You're not going to lose any mass. So whatever the new isotope is and the new element, it's going to have the same mass number. However, the atomic number is going to change, right? Because you're going to gain one additional proton. So the atomic number goes to 54, and if you look on your periodic table, the element with atomic number 54 is xenon, and it's going to be xenon 131. Okay, so those are kind of the rules of the game for alpha and beta emission. There's even though I spoke about gamma radiation, there's not really a a nuclear reaction that you can write for gamma radiation. You just need to know it's very high energy. But there's one other type of emission that I want you to know about, and that's called positron emission. What's a positron? We haven't really talked about that. Well, okay, here's an electron, and here's the symbol for the electron. A positron is the antimatter counterpart to the electron. So I don't know if you've heard of this in your prior experience with reading or television shows or science fiction, but there's this thing called antimatter. And antimatter is exactly like matter, except some of the quantum numbers are just a little bit different, are the opposite of what they are for regular matter. So for a positron, it's just like an electron. It's got 0 mass number, but instead of a negative charge, it has a positive charge. And if a positron and an electron ever come in contact with each other, because it's matter and antimatter, there will be complete annihilation, and you'll have 100% conversion of mass into energy. So that would be what's called a matter-antimatter conversion. Anyway, here's what's interesting. All right, positron emission involves a proton transforming into a neutron plus a positron. So it's kind of like the opposite of beta emission, where the neutron converted into a proton. With positron emission, it's a proton that turns into a neutron. And then in order to maintain conservation of charge, you have to have a positive charge, a positive particle pop out of there. Okay, so what's an example? Well, there is an isotope of carbon. We haven't talked about it much, but there's an isotope called carbon-11. It only has 5 neutrons and 6 protons. And when it undergoes positron emission, okay, so don't forget, one of these protons is going to now turn into a neutron. So the atomic number is going to go down by 1. Sorry, that's my daughter's playing. And so ask yourself, look at the periodic table. What is the element with atomic number 5? That's right, it's boron. And however, the mass number does not change. You've simply exchanged a proton for a neutron, so the total number of nucleons remains the same. And then that kicks off a positron. Positron emission is actually pretty important. You may have heard of PET scans. If you need to do like a brain function study, patients will they'll drink a solution with glucose in which some of the carbon atoms in the glucose molecules have been substituted carbon 12 for carbon 11, and that carbon 11 spiked glucose, when it gets absorbed into the brain, it starts to emit positrons. Those positrons can be detected through detectors in the instrument, and this is what allows positron emission tomography to happen. That's a PET scan. Okay, guys, that's it. Thank you so much for listening, and we'll have a good work session tomorrow. Okay, have a good night.